Okay, so this next set of lectures talks about cellular chemistry. So these are the learning objectives here. So part 1 is just an introduction to cellular chemistry. Here's a picture of the cell. This picture of the cell will come back on exams like the practicals, the exam 1 practical potentially, and possibly the final exam. So you should be familiar with all these different organelles and everything when we get to cell lecture 2, and that doesn't happen until week 3. For this week, we just start with the basic structures of the cell. So basic structures you'll see here, we've got the cell membrane, which is just the boundary of the cell. Then we have cytoplasm, which is everything that exists inside of the cell. And the cytoplasm consists of the cytosol, which is the liquid component, and organelles, which are the functional units of the cell. So in that cytosol is made up of a whole bunch of key elements. And here's a periodic table of elements. If you've never taken a chemistry class before, this may be unfamiliar to you, but all of these elements here on this left-hand side are absolutely essential in the human body. And we use these for all sorts of different things. For example, H is for hydrogen. We use that for regulating our acid-base balance. Na is for sodium. That's required for every nerve impulse, every muscle contraction. If you want to have a heartbeat, you need sodium. Potassium, same thing. So K is for potassium. You need that for every muscle contraction, every nerve impulse, all of that type of stuff. Magnesium is usually a cofactor for DNA-related substances. Calcium, we need that for releasing neurotransmitters from the end of a neuron. So we can go step by step through each one of these individual elements. What I recommend you do is memorize the element symbol and the name of that element. So you should be able to look at all of these symbols here and tell me what the name of that element is. Not for the entire periodic table, just for the ones that are listed here on the left-hand side. I promise you these will come back to haunt you if you are planning on going into advanced A&P or microbiology. We're going to expect that you can figure out that Na is sodium and so forth. So if we look at what an atom is made up of, an atom is made up of protons, neutrons, and electrons. Protons are positively charged particles in the nucleus of an atom. So this is kind of a diagram of an atom. This central part here is the nucleus of an atom, and protons are going to be the positively charged particles in there. Neutrons don't have a charge. They are neutral in charge. Electrons orbit around the nucleus in electron orbitals. Electrons have a negative charge. The atomic number is the number of protons in the nucleus of an atom. And that's also how we arrange elements on the periodic table of elements. So if we flip back to look at the periodic table of elements here, you can see that hydrogen here has number 1 for its atomic number. Helium has a number 2 for its atomic number. What this means is that there's 2 protons in the nucleus of helium. Now the mass number is the number of protons plus neutrons. So if we go back here, the mass number is this number down here. So mass number of 1. Well, since hydrogen has 1 proton, and the total number of protons plus neutrons is 1, then hydrogen doesn't have any neutrons. It's just 1 proton. The number of protons always equals the number of electrons in an uncharged atom. So for however many positively charged particles you have in the center, there's that many negatively charged particles floating around the outside. So if we want to determine the number of protons, neutrons, and electrons for something like sodium, so if we look at sodium, for protons for sodium, we would have Na11, and then it was, let's get the exact number here, 22.99, so we'll round that to 23. So sodium, this is sodium's atomic number, which is the number of protons. Sodium would have 11 protons, which means it also has 11 electrons. Now 23 is the mass number, which is the number of protons plus neutrons. So in order to get the number of neutrons, you would have to take 23 minus 11, and that gives you 12. So that's how many protons, neutrons, and electrons are in an atom of sodium. So if we wanted to draw out what sodium would look like, we would put 11 protons in the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We'd put 12 neutrons in the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we would start to distribute the electrons in electron orbitals. There are some rules for distributing electrons. Now in the first orbital that surrounds the nucleus, only 2 electrons can fit. So we'll put 1 here and 1 here. In each additional orbital, a maximum of 8 electrons can fit. So in the next orbital, we would have 1, 2, 3, 4, 5, 6, 7, 8. Now I distributed them like this in pairs for a very particular reason, and once we get into bonding, it'll make more sense why I did it this way. For now, we'll leave it like that. So we've put our 2 in the first orbital because the first orbital can only hold 2. And then we put our 8 in the next one because the next one can only hold 8. And we have to draw 1 more orbital because if you count, we only have 10 electrons so far drawn, and sodium has actually 11 electrons. So we're going to put that last electron floating around the outside. Now in order for an atom to be happy, it wants to have a full outer shell. Sodium's not happy. So sodium's got this one hanging out here. It wants to get rid of that. Well, if you lose this 1 electron, if you give up a negative charge, you're going to become positive by 1. So the charge of the sodium ion is Na 1+, or +1. So an atom is the building block of matter. An isotope. An isotope is an atom with a different number of neutrons. So it has a different mass number. The number of neutrons changes. So an example of an isotope. If we look at carbon, let's go back to carbon on the periodic table here. So carbon's up here. You can see that carbon has an atomic number of 6, a mass number of 12. So carbon, in its most common form, would have 6 protons and thus 6 electrons. And then in order to get the neutrons, you do the mass number minus the atomic number, so that gives you 6 neutrons. This is known as carbon-12, and again, that is another way of writing carbon-12, and this is the most common type of carbon that you're going to find on Earth. But we have this isotope of carbon, and it's carbon-13. And this has some medical relevance, which I'll get into a little bit. What carbon-13 is instead of having a 12 for its mass number, it's going to have a 13, which means carbon-13 has 6 protons, 6 electrons, but 7 neutrons. Carbon-13 is an isotope of carbon, and this carbon-13 happens to be radioactive. Now here's the medical relevance of this, and you don't have to pay attention to this if you don't care about the medical relevance, but it's kind of cool. So there's this type of bacteria known as Helicobacter pylori, and it can grow inside of your stomach. It actually thrives in acidic environments such as a pH of 2, which is how low your stomach acid gets down to when it's in full activity. So this Helicobacter pylori lives and thrives inside of your stomach in that acidic environment, can also tolerate pretty high temperatures, but that can cause stomach ulcers. So it actually eats the mucosal lining of the stomach and leads to the erosion of that stomach lining, which can lead to the development of stomach ulcers. Now, if you want to test a patient for Helicobacter pylori, one way to do it is through a biopsy of the stomach, but you can imagine the internal bleeding and the nicks and the possible secondary infections that can be caused by cutting into the stomach. So an easier way to test for H. pylori is using something called the urea breath test. So they take this radioactively labeled carbon and incorporate it into urea. Urea is a waste product that we give off in our urine, but certain microorganisms have the capability of breaking it down to ammonia and carbon dioxide. Now, if we have made in a laboratory urea that's laced with this carbon-13, what we do is we make the patient swallow it and know they're not swallowing urine, they're swallowing radioactively labeled urea, so it's different. So we make the patient swallow it, and then we wait a little while. And then as the patient breathes out, if they breathe out radioactively labeled carbon-13, what that means is that there was a bacterium inside of their stomach that broke down the urea, and now they're releasing radioactive carbon dioxide. Normal patients that don't have this bacteria would not be breaking down urea all by themselves. It's actually dangerous if people break down urea because ammonia can kill us. So if we had this capability of breaking down urea in the body, ammonia would accumulate, and that gets into the brain and causes us to slip into a coma. It kills us. It's highly toxic. So we don't want that floating around the body. So it takes a specialized type of bacteria to break it down. And if that bacteria is in our stomach, then we assume that it's Helicobacter pylori, because there's not a lot of other bacterial species that can survive our stomach acid like that, and that would be able to digest urea in order to release that radioactively labeled carbon dioxide in our breath. But anyway, so that's just one example of an isotope and how it's relevant to health applications. But an isotope is a derivative of an atom, so it's got a different number of neutrons, and an example is carbon-13. A molecule is when two or more atoms are bonded together, and a compound is when you have a mixture of molecules, so there's two or more molecules that are mixed together. So a compound could be like salt water. You've got sodium chloride, which is a molecule, and you have water, which is a molecule, and they're mixed together. So remember I drew out that picture of sodium. We'll go back to that. And here's sodium, and I drew out what its structure looks like, and it's got this free floating electron here. That makes sodium really unhappy. If it just got rid of that electron, it lost a negatively charged electron, then it would become positive by 1. And I said sodium plus 1 in its ionic form. An ion is a charged atom. So an ion is a charged atom. It's an atom that has either gained or lost electrons. So you have your atom that exists in its normal state that you'd find on the periodic table. But then when it starts to form bonds with other atoms to form molecules, then you start to see ions form, where one could lose an electron, the other could accept the electron, and that's where you have the development of cations and anions. Cations have a positive charge. One way that I remember that is I love animals. I'm a crazy cat lady. I actually prefer dogs. But anyways, so cat is in there. Cats make me happy. Cats positive. Cations have a positive charge. Anions have a negative charge. So sodium, where we have Na, and then we had the rings, and then on the outer ring we just had the one. When we lose that one electron, we're giving up a negative charge. So sodium becomes positive by 1. So sodium is known as a cation. If we draw out the structure of, let's do fluorine. So fluorine is 9. I'm not going to draw the protons and neutrons. We'll just draw fluorine, like the letter F in the center for the nucleus. Fluorine has 9 electrons, so fluorine, 2 in the first one, and then we would have 7 in the second one. Now I'm going to do this thing that I call the 4 corners method. I'm going to place electrons 1, 2, 3, 4, 5, 6, 7. So we're pairing up these electrons, and then you can see that there's one available here that's missing a pair. I always tell my chemistry students to think about it like electrons want to be married, so they want to marry each other. So these two are married, these two are married, these two are married. This one's unhappy, this one's not married, so that one wants to get married. Well, what fluorine can do is fluorine can actually accept an electron from someone like sodium that's willing to give it up. Now, if fluorine accepts this electron, it's accepting a negative charge, it's becoming negative by 1. So our ionic form of fluorine is -1. That makes it an anion. So cations have a positive charge, anions have a negative charge. Now, instead of drawing all of these out, I'm going to go back to the periodic table and show you how you can determine what the charges of the ionic forms of each of these are. Now, really, this only applies to the first 20 elements, but anybody in this row typically has a +1 charge. Anybody in this row is typically a +2 charge. Anybody in this row is a +3. And then we have this row, which is a plus or -4. It's kind of in the middle. Then in this row, it's a -3. This row is a -2. This row is a -1. So kind of going down, helium, lithium, sodium, potassium, and so forth would all have a +1 charge. Beryllium, magnesium, calcium, and so forth would have a +2 charge. We skip over these guys because they have weird exceptions. They do weird things, those transition metals. Then we go over here to boron and aluminum, and that's a +3. Then we have carbon here, which is + or -4. We have nitrogen, phosphorus, which is a -3. Oxygen, sulfur, selenium, which is a -2. Fluorine, chlorine, bromine, iodine, those are all -1 charges in their ionic form. And the ions form when they have somebody to take an electron from or somebody to give an electron to, when they're in proximity in order to form a bond. So I know some of this chemistry stuff is a little advanced, and if it didn't make sense to you when I was going through here, there's a couple worksheets that we'll do on this chemistry stuff in class. But other than that, you're not going to find a lot of the molecular structures or anything like that on an exam. It'll just be basic definitions. So if you know that a cation has a positive charge, an anion has a negative charge, you should be good as far as charges go. Just know basic definitions for this stuff. You will not have to draw out any structures or tell me how many protons, neutrons, and electrons are in each of these. So we talk about ions because they have a major relevance in cellular chemistry. the inside of the cell is different in composition than the outside of the cell. So you have extracellular fluid, which is the fluid that you'd find outside of a cell, and intracellular fluid, which is the fluid that you would find inside of a cell. If we look at the relative concentrations, outside of the cell and inside of the cell has the same osmolarity, or the same concentration of ions. But you'll notice there's a difference in composition. On the outside of the cell, you're going to find a lot more sodium and chloride ions. On the inside of the cell, you're going to find a lot more potassium, phosphates, and these negatively charged proteins. Now, another thing you're going to notice on the extracellular fluid is bicarbonate is much higher, but those are really the major intracellular and extracellular cations and anions. You should be familiar with where these are located. If I ask, what is the predominant intracellular cation? Well, the cation is the positively charged one. That would be potassium. If I say, what is the predominant extracellular anion? That would be either chlorine or chloride or bicarbonate. This is important when we get into how a nerve impulse is sent, or how a muscle contraction works. So being able to differentiate between what you'd find on the inside of the cell versus what is found on the outside of the cell, it's really going to help you later on, especially if you're planning on taking advanced A&P. For this class, minimally, you have to know these predominant intracellular and extracellular cations and anions. So just the ones that I've kind of boxed out here, you should be familiar with those. You do not need to know numbers, just the names of what they are. Here are some other applications of these ionic imbalances. So if we look at the first one, hyponatremia. If we look at the whole word hyponatremia, that's like a huge word that now you have to memorize, and you're probably like, oh, there's another term that we have to memorize for this class. But remember I said let's break down these words into their stems. Hyponatremia. Hypo means less. Na, Na, is referring to sodium. So this is a low sodium concentration. If you don't have enough sodium, this can lead to mental impairment, dilution of the extracellular fluid, or loss of sodium ions. Hypernatremia. Hyper means more. And A again is referring to sodium. Hypernatremia leads to coma, and it can be caused by dehydration. Hypokalemia. K is for potassium. If you don't have enough potassium, it could lead to increased heart rate, muscle weakness, and it's associated with insulin. So there's a redistribution of glucose going into the cell, potassium going out of the cell. So insulin fluctuations can affect can cause hypokalemia. Hyperkalemia. Hyper, too much potassium, leads to bradycardia, so a slow heart rate, initiated by ESRD. So actually, in practice, when we euthanize animals, we usually euthanize with an overdose of potassium. We give them an injection of potassium, which stops the heart, causes bradycardia. Hypochloremia is referring to not enough chloride. This can lead to alkalosis, and it's usually caused by prolonged vomiting or loss of sodium. Hyperchloremia can lead to acidosis, and it can be caused by bicarbonate loss or cystic fibrosis. There's also this chloride shift phenomenon that can happen where bicarbonate goes out and chloride goes in, and that can cause all sorts of issues inside of the cell. So all of these ionic imbalances cause major changes in the body.